Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is Chefina and Swap. The problem appeared in September Long Challenge 2020 and has a difficulty level of easy. The prerequisites for this problem are math and counting. The agenda for today is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see the approach to our solution and build the solution step by step, followed by which we will be seeing a pseudo code and then implementing our code in C++. The problem statement goes as follows. We are given a positive integer n and we have to consider the sequence s from 1 to n. Okay, and now we should choose two elements from this sequence and swap them. So for example, if n is given as 4, then we have to consider the sequence 1, 2, 3, 4, right? And we are allowed to choose two elements from this sequence and swap them. But further we are given that a swap is nice if there exists an integer m such that sum of first m elements of the resulting sequence is equal to sum of the remaining elements, that is last n minus m elements. So we are being told to find the number of nice swaps for a given n. So let's try it out for a small example, that is n is equals to 4. So for n is equals to 4, we know that the initial sequence is 1, 2, 3 and 4 and we can choose two elements and swap them. For example, if I choose 1 and 3 and swap these two elements, my resulting sequence will be 3, 2, 1 and 4. And in the resulting sequence, I can see that sum of my first two elements, that is 5, is equal to sum of the remaining elements. So this is a nice swap. Similarly, if we swap 2 and 4, the resulting sequence will be 1, 4, 3 and 2. Again, we can see that the sum of first two elements is 5 and sum of last two elements is 5. So this is a nice swap. So for a given n, we have been told to find the total number of nice swaps possible. So coming to the constraints of the problem, it is important to note the constraints, as in this question a brute solution is never going to work. Why? Because a brute solution involves finding all possible swaps, right? And further checking if that swap is a nice swap. And we can see here that for the smallest subtask, n goes up to 10 to the power 3, and finding all swaps essentially means that finding all pairs, which is nothing but n choose 2, right? So if we perform these many number of steps, and after that if we check using n more iterations that if the swap is a nice swap, this will result in a complexity of n cube, which in our case will go up to 10 to the power 9, which is not intended in the question. So a brute solution is never going to work in this problem. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. So now that we have read the problem and understood it, let's start building up our solution with an observation. So the observation is as follows. Remember that we are going to be given an integer n and we have to consider the sequence s, that is 1, 2, 3 up to n, right? So the observation goes as follows. As we know that after performing the swap, we have to make two partitions of the sequence such that sum of the first m elements is equal to sum of the remaining elements, right? That is, if the sum of first m elements is, let's say, 27, the sum of other remaining elements should also be 27. Only then the swap can be called as a nice swap. Similarly, if the sum is, let's say, an even number, for example 14, then the sum of the remaining elements must also be 14. That is, in either case, you observe that if the sum of one partition is odd, then sum of the other partition must also be odd. And if it is even, then the sum of other partition must also be even. In either case, you observe that the total sum, that is, the sum of all elements in the sequence, is always going to be even. Why? Because even odd plus odd is even, and again even plus even is also even. So we can say that if the given sequence 1 to n, thus if sum of all these elements, that is 1 plus 2 plus 3 up to n, if this sum is odd, then there is no way we can perform a swap that is nice. So the answer for such n is going to be directly 0. So this is going to be our observation, which is going to help in building the solution. To take a small example, let's say we have n is equals to 5. So the sum of all elements, that is 1, 2, 3 up to 5, that is 1 plus 2 plus 3 plus 4 plus 5 is going to be what? It is 15, right? And we can see that 15 is an odd number. So we cannot possibly partition it into two parts such that they have same parity. So straight away we can say that the answer for n is equals to 5 is what? 0. So now that we have seen the observation, let's go to the solution and see that what possible cases are going to contribute to nice swaps. So starting off, what if there are already two partitions in the given sequence which have equal sum? What do I mean by that? That for example, we are given an n and the sequence will be what? At the beginning, it will be 1, 2, 3 up to n. And what if there are already two partitions whose sum is equal, right? So that is, the sum is s, and here also the sum is s. So what in that case, how is it going to contribute to our answer? So to take an example, we have n is equals to 20. If for n is equals to 20, if you calculate the sum of first 14 elements, that is 1 plus 2 up to 14, and the sum of remaining elements, that is 15 plus 16 up to 20, if you calculate, both of these sums are equal and equal to 105. Right? So already the sums are equal. So we can perform any number of swaps amongst these 14 elements, right? And any number of swaps amongst these remaining 6 elements. So what will be the total number of swaps here? The total number of swaps will be 14 choose 2, and in the second partition it will be 6 choose 2. So to generalize, let's say that this pivot element, let's call it x. So in the first x elements, we can perform x choose 2 number of swaps, and in the remaining elements, we can perform n minus x choose 2 number of swaps. But how to find this pivot element, that is x? We will soon see that how to find this pivot element. But the point is that if we have a sequence wherein already there are two partitions with equal sum, they will contribute at least these many number of nice swaps to the answer. There are more swaps which can also lead to same sum. We are going to see them soon. So now the question is, what if there are no two partitions such that their sum is initially equal, right? So in that case, we need to make a single swap so that we can get two partitions whose sum is equal. What do I mean by that? Let's see through a small example. For example, I have n is equals to 7. For that, my sequence will be 1, 2, 3, 4, 5, 6, and 7. And I can see that the sum of this partition is 10 and sum of this partition is 18. And what is the ideal sum that I am aiming for? The total sum from 1 to 7 is 28, right? So ideally my both sums should be 14 and 14. So as we can see that the first partition is deficit by 4 and the second partition has extra 4. So here I can see that if I swap 1 with 5, I can get a good sequence. That is, the swap will be nice. Why? Because by swapping 1 and 5, I will compensate this difference of 4 on either side. Right. Similarly, I can also swap 2 with 6 and 3 with 7. So what's so special about these initial partition that we made, right? I could have also made the partition like 1, 2, 3 and remaining elements on the other side. But what will happen in this case? Thus, their initial sums will be as follows. The first partition will have the sum as 6 and the other partition will have the sum as 22, right? So in that case, you see that the first sum is deficit by a margin of what? By a margin of -8, and this sum exceeds by +8. So in no way can I swap a number from the right partition such that it makes up for this difference of 8, right? Because 8 itself is greater than my given n, right? So I cannot take such smaller partition as my left partition. Similarly, I can also not take a bigger partition as my left partition. For example, I cannot include 5 in my left partition, right? Because if I include 5 in my right partition, sorry, if I include 5 in my left partition, what will happen is that the first partition will have the sum as 15 and the second partition will have the sum as 13. So this first partition now exceeds by the sum by 1, the desired sum 14 by 1, and the second partition has a deficit of -1. So I can never swap a number from the right partition and make the sum go down, right? Because I will always be swapping with a bigger number. So the sum can always only go up. So this is also not possible and neither are such cases possible. So ideally, we need to find the biggest possible partition from left hand side such that its sum, let's call this sum S1, okay, and the right partition sum as S2. So we need to find a partition big enough from left side, that is S1, whose sum is as close as possible to the ideal sum and at the same time it is less than or equal to the ideal sum. Okay, so in this case we can see that the ideal partition is what? Consisting of first 4 elements and the right partition consists of the last 3 elements. So what we just saw is that if we have a big enough partition on the left hand side with sum very close to desired sum and it is also less than or equal to the desired sum, then we can perform systematic swaps like swapping 1 with 5, 2 with 6 and 3 with 7 to make the sums equal. And why the sums will be equal? Because when we swap 1 with 5, we are essentially adding 4 on the left partition and we are removing 4 from the right partition. So essentially the sums will become equal, right? So in the same way, whenever we swap 2 with 6, the same thing happens. Whenever we swap 3 with 7, again the same thing happens, right? So these are systematic swaps. But the question is again how to find this left partition in the first place, right? So let's call this pivot element as x. So how do we find this x? Because if we find this x, we know that the remaining elements on the right hand side can be systematically swapped with the elements on the left hand side so that the sums can be made equal. So if we have x, we know that the remaining elements are n minus x, right? And in that case we can observe that we can make exactly n minus x swaps and make these sums equal, right? So the question now is how to find this x. So now to find x, let's say that for given n, the sequence will be 1, 2, 3 up to n, right? And let's define a variable sum which contains the sum of all these elements, that is 1 plus 2 plus 3 up to n. So this will be what? It will be essentially n into n plus 1 by 2, right? This comes from math. And now there will be the pivot point x somewhere in between. We don't know exactly where, right? But we do know that sum of first x elements is going to be what? It is going to be x into x plus 1 by 2, right? And we want this sum to be as close as possible to sum by 2, right? So we can form a mathematical equation that is x into x plus 1 by 2 is equals to sum by 2, so that whatever value of x we get from this equation leads us to the pivot point. So there can be two possibilities here. We will discuss both of them. On solving this quadratic equation, either you can get the value of x as a perfect integer, or you can get a decimal value, right? What do these two things mean? If you get x as an integer value, it means that there already exists a partition for which the sum is equals to sum of the remaining elements, right? But if you get a float number, we would have to take the floor of that x so that we get our pivot point, right? So once we have the value of x, we can calculate the number of swaps, that is n minus x, right? As discussed in the solution. But wait, we have to revisit the case of n is equals to 20, because in that case there was already a partition with equal sum. What will happen in that case? Let's see. So for n is equals to 20, initially the sum of first 14 elements was equal to the sum of last 6 elements, right? And the sum was equals to 105 and 105. But what if we include 14 in the right segment? That is, the first segment is of 13 elements and the remaining segment is of 7 elements. In that case, what happens is the sum of the first 13 elements will be 91 and the sum of the remaining elements will be 119. So we have created a difference of minus 14 over here and a difference of plus 14 over here. So in the cases wherein the sum was initially also equal, we can create partitions and fulfill that deficit of 14 by making swaps uh, in between the left and the right partition, right? How we can do it? Here we can swap 1 with 15, 2 with 16, and so on. That is systematic swaps, right? So independent of whether you get x as a floating point or integer, it is going to always contribute n minus x swaps towards your answer. Why? Because n minus x is the number of elements that are going to be swapped with the elements in the left partition, right? And in special cases like n is equals to 20, where there exists a pivot for which the sum 105, for example, is equal to the remaining element sum, that is 105, in that cases they will additionally contribute in the following way: x choose 2 plus n minus x choose 2, as discussed in the beginning of our solution. So now that we have seen the solution in detail, let's get to the pseudocode. The pseudocode goes as follows. First, we will take the input for n, and quickly we will check that if the sum from 1 to n is even or odd. If the sum is odd, then the answer is definitely 0 and we print it and continue. Else, we find x, our pivot point, using the quadratic equation that we had formed, and as soon as we find x, we include n minus x nice swaps in our answer. And then after that, we check if the special condition is true. That is, if the sum of first x elements is exactly equal to the sum of the remaining elements, then we additionally add these many swaps in our answer as discussed in the solution. And Finally, we print our answer. So now that we have seen the solution and the pseudocode, let's get to the implementation part. So we start off by taking the input for t test cases, and in each test case we take the input for n. Now once we have taken the input for n, our first task is to see whether the sum from 1 to n is even or odd. So we do it by writing an if condition. So if n into n plus 1 by 2, if this quantity is odd, it means that our answer is 0. So we can directly print the answer and continue with our next test case, right? But if the answer is possible, then we have to find the value of x, that is the pivot element, right? So I create a variable x and find its value as work of n. What is work? Work is a function that I am going to define outside my main function so that it returns me the value of x from the quadratic equation that we had formed while seeing the solution. So the work function is as follows. So if you see, this formula is what you are going to get if you solve mathematically the quadratic equation that we had formed during the solution. So once we have this value of x, we can add n minus x to our answer. So let me create a variable answer as well and initialize it to 0. So once we have x, we know that this x contributes to our answer minimum n minus x nice swaps, right? And now we have to check if the sum of first x elements, if it is exactly equal to the sum of the remaining elements, then we have to add additional x choose 2 and n minus x choose 2 moves or swaps to our answer. So how do we do that? We do it by the following code. So if this condition is satisfied, it means that sum of first x elements, that is x into x plus 1 by 2, is equals to the sum of the remaining elements, right? So if this condition is satisfied, we increment our answer by x choose 2 and n minus x choose 2. So I have written a function known as n choose 2 here, which will help me calculate the value for x choose 2 and n minus x choose 2. So let me define it here. The function returns the value of n choose 2, and that's it. Now that we have written the function n choose 2, we have completed calculating all possible nice swaps and included it in our answer variable. So now the only task remains is to output the answer and give a new line character as asked in the question. So without wasting any time, let's check this solution by submitting it on the CodeChef ID. Great, so our solution works. The complexity of the code that we just wrote is O1. It means that we are using constant number of computations per test case. So there will be no problem to solve the question in the given constraints and in the given time limit.